Imagine shrinking down, way down, smaller than a grain of sand, smaller than a speck of dust, smaller even than a single cell. You have now entered a realm where the rules of our everyday world, the rules of throwing a baseball, the rules of driving a car, simply fall apart. This is the quantum world. It is the universe on its smallest, most fundamental scale. Quantum physics is our instruction manual for this bizarre and beautiful place. It is the science that describes the behavior of atoms, electrons, photons. And let me tell you, their behavior is nothing short of mind-blowing. In our big, comfortable world, things are predictable. If you drop a ball, it falls. We know where it is. We know where it is going. We know how fast it is moving. Newton laws give us a sense of order and certainty. But down in the quantum realm, certainty is a luxury the universe does not afford. Particles can seem to be in multiple places at once. They can vanish from one spot and reappear in another without traveling the space in between. It is a world of maybes and probabilities, not of definite yeses and nos. It is a reality that seems more like a fantasy novel than the solid ground we stand on. This journey into the quantum world is not just a trip for physicists in lab coats, it is a journey into the very fabric of reality itself. Everything you see, everything you touch, you yourself, it is all governed by these strange quantum laws. The light from distant stars reaching your eyes, the chemical reactions that power your body, the computer chip in the device you are using right now, all of them are quantum phenomena. To understand the cosmos, we must first understand its smallest, most mysterious components. It is a universe that operates on a logic that defies our common sense, inviting us to expand our minds. So, buckle up. We are about to take a ride on the ship of the imagination into a universe hidden within our own. We will explore a place where particles dance to a rhythm of pure possibility, where reality itself seems to be waiting for someone to look at it before it decides what to be. We will peel back the curtain of the familiar and peek at the cosmic machinery humming away underneath. It is a place of deep mystery, but it is also the foundation of everything we know. The quantum world awaits. Before we dive into the deep end, let us get to know the locals of this quantum neighborhood. The main characters are particles. Think of them as the universe Lego bricks. Everything is made of them. Your body is made of atoms, protons, neutrons, electrons. The light that lets you see this page is made of photons. These are the fundamental bits and pieces of existence. In our everyday world, a particle is like a tiny solid ball, a marble. It has a definite location. It is here, not there. Simple, right? But in the quantum world, things get fuzzy. Particles have a dual identity. Sometimes they act like marbles. Other times they act like waves. Imagine a ripple across a pond after tossing a stone. A wave is not in one spot. It spreads out, peaks, troughs. Waves can interfere with other waves, creating interference patterns, crests, valleys. A quantum particle, like an electron, can be both a particle and a wave. This is not just analogy, it is reality. Wave-particle duality is a core rule of the quantum club. It is like saying your best friend is solid and also liquid at the same time. It does not make sense in our world. For an electron, it is just another Tuesday. This dual nature unlocks the other mysteries we will explore. When a particle behaves like a wave, it is not at a single point. Its location is a spread-out field of possibilities. A wave of probability shows where it might be found. The quantum world is the domain of these shapeshifters. Solid, predictable objects dissolve into shimmering waves of potential. The atom is a perfect example. Diagram. Atom with nucleus and an electron shown as both dot and wave. Electrons are not tiny planets orbiting neatly. They exist as cloud-like waves of probability, orbitals. The quantum world is not a mini version of ours. It is a different kind of reality. So this idea of a particle being in multiple states at once has a name, superposition. It is one of the cornerstones of quantum mechanics. Before we measure it, the electron is not just at the left slit or the right slit. It is in a superposition of being at both. It is not that we just do not know where it is. It is that the electron itself has not settled on a single position. Its reality is, well, a fuzzy blend of all its potential locations. It exists as a wave of probability, which is basically a mathematical description of all the places it could be. Think of it like a spinning coin. While it is in the air spinning, it is not heads and it is not tails. It is in a dynamic, blurry state of both possibilities. It is only when it lands on the table, when we measure it, that it has to be one or the other. Superposition is the quantum version of that spinning coin. The electron is in a superposition of went through the left slit and went through the right slit. When it hits the detector screen, or when we place a detector at the slits, the coin lands. The superposition collapses, and reality picks one outcome from the menu of possibilities. This is, fundamentally different from our everyday experience. If you hide a red ball under one of two cups, its location is a matter of ignorance. The ball is definitely under one specific cup, you just do not know which one. But for a quantum particle, its location is a matter of true indefiniteness. Before measurement, it literally does not have a single, precise position. It exists in a haze of potential. This is a profound shift in our understanding of reality. Objects do not just have properties, their properties can be undefined until the moment they are measured. So when a scientist says a particle can be in two places at once, they do not mean two tiny copies of the particle exist. They mean the particle existence is described by a wave function that is non-zero in two different places. This wave function contains all the information about the particle. It tells us the probability of finding the particle at any given point if we were to look for it. The particle is the wave, and the wave is spread out. Until the moment of measurement, the particle truly is its cloud of possibilities. The collapse of the superposition brings us to another pillar of the quantum world: uncertainty. Werner Heisenberg's famous uncertainty principle says there is a fundamental limit to what we can know about a particle at once. You cannot know a particle's exact position and its exact momentum. Momentum equals mass times velocity at the same time. The more precisely you measure one, the less precisely you can know the other. It is not an instrument problem. It is built into the universe. Imagine measuring an electron position. To see it, you must interact with it, maybe by bouncing a photon off it. An electron is so tiny that even one photon gives it a big kick, changing its momentum unpredictably. For precise position, you need a high-energy, short-wavelength photon, but that gives an even bigger kick and makes momentum more uncertain. A cosmic trade-off you cannot win. This is not like a weather forecast. A meteorologist might say 70% chance of rain because of incomplete data. With perfect data, you could predict weather exactly. Quantum uncertainty is different. It is inherent, irreducible fuzziness. The universe runs on probabilities. It is not just missing info. It is fundamentally probabilistic. Einstein said, "God does not play dice, but experiments show the dice are always rolling." The double-slit lesson: when the electron path is unknown, position uncertain, it behaves like a wave and makes an interference pattern. Its momentum is more defined. Measure its path, pinpoint it at a slit, and you destroy the wave behavior. Knowing position with certainty makes momentum wildly uncertain, so the interference disappears. The universe forces a choice. It will not let us know everything at once. After hearing all this, you might be wondering, if all the atoms that make up my body are governed by these weird quantum rules, why cannot I be in two places at once? Why do not I behave like a wave and just pass through a solid wall? It is a great question, and the answer lies in the vast difference in scale between one electron and the trillions upon trillions of particles that make up a baseball, a planet. The strange quantum effects are still there, but they get completely washed out in large objects.